Thank you, Jan, Gerd, and the Fetzer Fund for organizing this, putting this all together. That's it still shows my site. Doesn't matter, huh? Yeah, probably okay. Yeah. So it's about quantum optics with complex molecules, in particular nanobiological matter, and I will spend a few slides on explaining why this is interesting to us, at least. But you may, in the meantime, feel like sitting in the wrong conference, because it's about quantum optics, but there's a good portion of it also on physical chemistry and biomolecular physics. But I'll try to guide you through that. Good. So, I would like to. Okay, now it works. Before starting with the real physics, of course, I have to introduce the team, because otherwise I would forget it in the end. As you can see, we're working at the University of Vienna. And, well, the group is changing all the time, therefore I cannot show everybody who contributed to the different projects, but in the course of the talk, you will see them mentioned with the papers. So, but that's currently the team, and they're working on the different sub-projects, color-coded here, for those who know that already. So, and the collaborators in particular on these projects are Marcel Mayer, Valentin Köhler, chemists in Basel who are producing biomolecules for us, and we have a European project on nanoparticle interference, where also Angelo Bassi, who is sitting somewhere here, hi, is member and part of it, and Ori Czechnovsky, Uzi Evan, Klaus Hornberg is a theorist. All right. Let's start with the general idea of all these experiments. And usually, a while ago, I did not introduce the experiments with the Schrödinger cat, but Nicolas Gisin encouraged me indirectly or directly to stick to that image somehow, as you will see. So and it's very related to the biological aspect afterwards also. So the question is, what is Schrödinger's cat? Huh? And Schrödinger's cat is actually, well, something very complex. Huh? A real cat is complex, and it should, as I would say, at least contain one biomolecule. Huh? It is certainly also warm, and that is also the case in all our molecules. It must be in two different states, which are clearly discernible, clearly distinct. Here it is dead and alive. In our case, it's a particle being in two different positions, which can be clearly distinguished. Actually, there's a small side remark, because Schrödinger's cat would only have survived in its natural environment. In the box, isolated from the environment, it would probably have died anyhow. So the question is how to keep it in a living environment, or a life-sustaining environment. And as many point out, it should also symbolize entanglement, and that was sometimes what kept me away from claiming that this is a real cat, what we're talking about, but I'll make the analogy more explicit here. So it's about trying to get biomolecules in superposition states of two different places at once, so to say. And of course, a molecule is something complex. In our experiments, typically, still it consists of something up to 1,000 atoms per particle covalently bound. And of course, you may write this as an entangled state with a vacuum, where n atoms, 800 atoms or so, are sitting on the left-hand side and nothing on the right-hand side, and or on the vice versa. So 0 here and n here. And so there are maybe very many atoms, and we're trying to scale that up to many thousands of atoms. And actually, our molecules are still very hot. Typically, when we launch them, they're at about 500 Kelvin. They will need to be colder in the future for coherence and decoherence reasons. Then a superposition, not of dead and alive, of course, but in a superposition of positions, typically separated here by a few hundred nanometers up to a micrometer. And the question is whether we can also do that with self-replicating objects. Probably not self-replicating in free flight, but in principle, such as plasmids or viroids. A viroid is not a virus itself, it's just the RNA code, but in principle, if you inject that into a plant, it can also replicate. But that's a question for later. And then entanglement exists in two different forms. On the one hand, you may say this is an entanglement with a vacuum, but later, if there's decoherence, of course, that's a very natural entanglement process also that we unfortunately often see. So what are the key motivations for us to do this with biomolecules instead of metal clusters, organic other stuff that we had in the past? So on the one hand, as an experimentalist, for us, or for me, it's really an intriguing experimental challenge. Can we do it? And it's very hard to get that done with peptides, proteins, and DNA, mostly because you need new molecular beam methods. It's not so easy just to make a thermal beam of proteins. They denature, they fragment, they wouldn't survive. Huh? So the question is, how do you get them into the gas phase? And a part of the talk will be about that. You also need different coherent manipulation schemes. You cannot just take a mechanical grating for something that has a dipole moment of 300 dBi. And you cannot just take an ionization grating on a protein that simply doesn't ionize with a single photon. So the question is, how do you do that? And you need refined detection methods. And although, of course, many people have been interested in biomolecular physics in general, all the mass spectrometry community in the pharmaceutical industry, they're interested in ions instead of neutral particles. But for quantum optics, we're interested in neutral particles, and therefore the detection methods also have to change. The advantage for us, one motivation for using these things is also that biology is a kind of natural nanotechnology. Nature has selected certain species, certain molecules to exist in well-defined masses and shapes and configurations. And in a certain sense, it may facilitate even the experiments at high mass interference that we are often talking about. And so besides these technical things, there are many applications for us where we are motivated in that. And well, I call this molecular metrology. It's not metrology in the sense that some atom interferometer people are talking about it, or what you can do in laser physics. When we are talking about metrology, we're interested in measuring properties with a % or better precision. But that is already an achievement in many cases because many of these molecular properties have not been measured very accurately. And you will see a bit further down how we do that. But in principle, we can access polarizabilities, optical absorption spectra, magnetic either dipole moments or susceptibilities. So that gives us information about the aromaticity of these molecules. An important function is how do these molecules change as a function of hydration. So if you start in the native, not native, but in the naked state where the isolated molecule is sitting in the vacuum, it may change its configuration, its shape, as a function of the number of water molecules that you add to it. And the question is, can you do that without destroying quantum coherence? Will there be evaporative decoherence or not? So there are many open questions, but we think that this is important to study the question whether we can really bring Schrödinger's cat in a biomimetic environment that the molecule does as if it was in a real bio-sustaining environment. But that's also related to decoherence, because with this hydration shell, of course, there are many potential decoherence mechanisms. So that is on the small scale with particles, say, below 2,000 mass units. And then the other question is, can it really be done with something super complex, with proteins and DNA and so forth? And we're working on sources right now, and you will see the status in a minute. All right, so, but before we start with the quantum part, I really have to go through this physical chemistry part, because that's really keeping us pretty busy at the moment. So we start with different molecules. As you know, biology is very rich, and we're mostly interested at the moment in polypeptides, proteins, DNA strands, vitamins, and things like that. And what our friends in Basel have been preparing and are still preparing is functionalized polypeptides with the goal to bring them into the gas phase just by evaporation. And as you know, typically you cannot do that. You cannot just cook an egg and hope that the egg will fly. But actually you can do if you help the egg a little bit. So if you take the peptide and functionalize it. So what keeps the peptides together? That's mostly charges, it's electrostatic forces. And you can start by taking away the Zwitter ion character by neutralizing it somehow, functionalizing. They also tried methylating and in the end perfluoroalkyl functionalizing these polypeptides, and that actually seems to be a very good approach. So I won't show detailed pictures here, but the good message is functionalizing polypeptides really helps getting them into the gas phase. But that's really just starting off right now. Another method is actually even new in physical chemistry somehow, and that is laser-induced acoustic desorption. So the question is, can you combine thermal methods and acoustic methods to launch biomolecules in vacuum? And we tried that with chlorophyll here, and actually with many other molecules. And the idea is to deposit the molecule as a powder, first as a solution, which is being dried in vacuum, and then shine a laser on the backside of a thin foil, a 12 micrometer titanium foil, for instance. So the laser will not interact with the molecules directly, but it will heat the metal on the backside. And if it does so, there's a kind of plume going off on the backside, which gives a kick and thermal stress to the upper side, which releases the molecules. And so that works. It works for the chlorophyll here, which is a very fragile molecule, actually. It typically splits here, which you can see. It actually does that also in our case, but it also goes off as an intact molecule. And we've seen that we can also photonize it very nicely. So in principle, chlorophyll is a good candidate for interference experiments. The nice thing in general about this method is that molecules go off very slowly. For particles in the range of 10,000 mass units, they can be as slow as 20 meters per second, which is good. The beam intensities are still a bit challenging. We've also been working and are still working on electrospray ionization. That's a method that won John Fenn a Nobel Prize more than 10 years ago. But it's nowadays routinely used in chemistry and mass spectrometry. And the idea is that you fill biomolecules in a solution, and if you apply a voltage between a thin capillary with the solution inside and an opposite counter electrode, then a small cone will form, and that splits in many droplets. These droplets evaporate, and because of the excess charge, they explode, evaporate, explode, evaporate, explode, until you're left with a single biomolecule inside. You can see how the spray looks in reality, and for instance, with myoglobin, we've seen very nice signals. So in principle, we can get them into the gas phase, about 10 to the 6, 10 to the 7 per second. But as you can also see, they're still highly charged. That's part of the process. So what we're working on right now is to reduce these charges. But it's also very natural that's a polypeptide here in the same machine, but what is very natural is to add water in this machine. So that's very easy to do then. And last but not least, with the methods, you can laser desorb molecules directly from a powder in a supersonic jet or in a buffer gas. That's also something we're playing with. And we did that with polypeptides again, up to the antibiotic remicidin here. And that works very nicely, generates very nice signals. But again, that's only source development so far. It's very close to being connected to the interferometers very soon. So that keeps us busy, but that's not the quantum part yet. So the question is, once we have these sources, what can we do with these things to see their quantum nature, quantum wave nature? And in principle, in our group, we have 3 different setups for that. There's far-field diffraction, just the textbook example of diffraction at a grating. The second one is what I want to spend more time on, is the Kapitsa-Dirac-Talbot Law Interferometer, which is a near-field interferometer with 3 gratings. And finally, also an interferometer with 3 photoionization or 3 optical photodepletion gratings. But the general, outside of all these experiments, the general outline is that you have to have a source. So far, it still used to be a thermal source, an oven, but that will be replaced by some of the other sources that I mentioned before. Then you have to have, 3 gratings in our case, and I will explain in a minute why. Finally, you need a detector, which is electron impact quadrupole mass spectrometry, but that can be anything else. Also, it can be time of flight measurements with laser ionization or fluorescence detection, which we also have. But the key of the interferometer is that we have to respect the fact that there's no coherence in the molecular beam in the first place. So there's hardly any velocity selection, and there's hardly any any spatial coherence in the beam. The de Broglie wavelengths of these things, of these molecules, when they're traveling at 200 meters per second or so, range between 10 to minus 13 and a bit more than 10 to minus 12 meters. It's very, very tiny. And we're heading for 10 to minus 14 meters. So it's really tiny. And there's no coherence whatsoever in the very beginning in the source. So you have to prepare that by the first grating. The first grating is a position selector, if you wish, a periodic position selector, which, by virtue of Heisenberg's uncertainty principle, makes that there's a strong confinement here, which leads to a spreading of the wave function and the spreading of the momentum distribution. And the spreading is such, or the distance between the gratings is such that there's sufficient time to overlap in the end between the wave function overlaps at least 2 or 3 of these nodes and antinodes in the grating. The second grating is a phase grating, so that spreads out here. Is a phase grating where the laser field of the laser interacts with the polarizability of the molecules. We have different types of gratings also. They can be ionizing, they can be fragmenting, there may be different types. But here it's a phase grating that just imprints a phase, doesn't take away any molecules, but imprints a phase. And this phase modulation of the matter wave evolves into a density distribution, a molecular density distribution in free space, a flying nanoruler, if you wish, which can be probed and sampled by the third grating, which is scanning here across the grating. And if you just count the molecules that pass through the third grating, you see the interference pattern coming up, which in this case has a sinusoidal shape that's related to the open fraction of the grating, could be slightly different also. We call this a Talbot Law Interferometer because the spacing between the gratings is chosen such that in the near field there are these self-images which Henry Fox Talbot had seen in optics already 200 years ago. But in matter wave interference that is new, relatively new. John Clauser did that with atoms already in the 90s, but otherwise with molecules we're still the only group. And our mass and complexity record, if you wish, is still, unfortunately still, but at least it's this guy here, a molecule which is a perfluoroalkyl functionalized tetraphenyl porphyrin. It has 810 atoms, a mass of a bit more than 10,000 mass units, and it interferes very nicely, shows high contrast quantum interference. You see the fringe visibility here, which is in full agreement with what we expect from standard quantum mechanics. Knowing the properties of the molecules, the polarizability and absorption cross-sections roughly. That is already very close to something very biological like cytochrome C. In mass, that's about the same thing. But so far, we didn't have really the source to do it with cytochrome C. And as briefly mentioned in the beginning, we're getting close, but it's not yet implemented. What has been implemented and seen already is a series of interference experiments with vitamins, like vitamin E, A, D, then retinal resveratrol, whatever you like. So a very healthy experiment. And these particles are not at all symmetric, and they rotate not only here on the screen, but also in real life, 10 to the 10 times per second. They vibrate on the picosecond timescale, and nevertheless, they all show very nice high contrast interference. Now, of course, we can extend these experiments to zillions of molecules because there are virtually zillions of molecules out there. But we focus on a few of them because we want to measure their properties. In the past already we had various measurements, not on these molecules, but on others, where we could show that you can measure polarizabilities, dynamic dipoles, conformations, and absolute absorption cross-sections, and various other things. I just want to illustrate that on one example here, where the data are still for fullerenes, but we are just trying this right now with carotenes. So the idea is that you generate this nanoruler in free flight by virtue of this Talbot Law interference configuration. And so that generates a fringe pattern that you can see here. And any relatively weak interaction, but it's not weak measurement, it's a relatively feeble force that interacts with the molecules may shift the interference pattern. And this shift can be detected very efficiently. In principle, you can see a few nanometer shifts of the interference pattern. It's a matter of signal to noise. In principle, it could be better. And so what kind of forces can you have? You can have dipole, you can have electric field gradients, magnetic field gradients, you can have a laser beam coming here, and photons can be absorbed. And the sensitivity is so high that even the absorption of a single photon by a single molecule will shift the interference pattern of this respective molecule. Actually, on average, we look at an absorption of 0.14 photon per molecule. And so the shift of the interference pattern can be seen, actually reduces the contrast and gives us the possibility to derive cross-sections very precisely on the molecular level, not on the atomic level, but it's on the, actually can be better than that here, can be on the 1% level. But on beams which are extremely dilute, we have a typical density of 10 to the 6 per cubic centimeter. And if you wanted to do a classical absorption measurement with a photon being sent through a cell and measuring the transmitted photon flux after or behind the molecular beam or molecular cell, actually, if you wanted to do that in a classical way, you would have to have a cell which is 1 million kilometers long. And here you can do it on a millimeter wide beam. So it's because you interact and talk to every molecule. Why could that be interesting, or how could you extrapolate that to something relevant for life? For instance, photoisomerization processes are very important for life. If you think about retinal, that's what gives you your vision, that a photon is absorbed by the retinal molecule and deforms rhodopsin in your eye. But it's also important in the formation of actually vitamin D3 from dehydrocholesterol. And many of these processes are very poorly studied in the gas phase, and then as a function of hydration, for instance. And since we can see the single photon absorption, the hope is that we can see that really on the single molecule level soon. Yeah, well, that's just adding to that. In some cases, in particular, if you're interested in time-resolved processes in the molecules on the nanosecond scale, then it may be better not to use the KDTLI that I had been mentioning before, but the Ultima interferometer, which is a 3-pulse photodepletion grating interferometer that you will see here. And the idea of that is, well, mechanical gratings work, optical phase gratings work, but you can also build absorptive gratings for molecules by a standing light wave in the ultraviolet range, vacuum ultraviolet range, at 157 nanometers. And in that case, what happens is either that you ionize the molecules in the antinodes of the standing light wave, or you can even split off a part of the molecule in the antinodes of the standing light field. Well, these gratings can have an extremely small period. If you have a 157 nanometer fluorine laser, the period of this grating is 80 nanometers, roughly. And the grating is on only for a very few seconds. But you can combine, nevertheless, 3 of these gratings for a full interferometer, which is now operating, well, both in space, but in particular also in the time domain, so that you can follow dynamic processes. The interferometer that has been set up in our lab can tolerate at the moment de Broglie wavelengths of 200 femtometers, which is, again, very small, if you think that most of our molecules are a few nanometers big. But so this interferometer has been used already for anthracene clusters in the very first experiments, but meanwhile also on a number of biomolecular clusters like vanillin, caffeine, and in principle it should work very nicely with tryptophan clusters, and it will certainly be used very soon on polypeptides, antibiotics, and things like that. Voilà. And with that, I come already to the summary. So what we're doing is somewhere at the interface between quantum optics and physical chemistry at the moment. We have a number of interferometers, actually 3. The Kapitsa-Dirac Talbot Law Interferometer, which has a optical mechanical grating. the ultima interferometer, which operates with 3 optical gratings, and far-field diffraction, which is not shown here, on a single grating. In the past, that was used mostly for organic but not naturally biological materials, but now we're really working on the sources to get peptides, DNA, and proteins into the gas phase and making good progress there. And with that, I thank you for your attention, and I'm open for questions. Thank you.